Hey everybody, in this video I'm going to walk you through some of the wavelength, frequency, and energy calculations that you can do for the electromagnetic spectrum, or at least different regions of it. In this particular example, we're going to say, what if you had a wave whose wavelength, so from one peak to the next, was 8 picometers. That's an extremely teeny tiny little wave. But we're going to walk through what that means in terms of the frequency of the wave, the energy of the photons that make up that wave, and so forth. So let's first just deal with the fact that this measurement is given in picometers, and that's because it's a extremely tiny wave. So you would need a very small measurement like picometers to really keep track of it. But to do any calculations with that wavelength as a starting point, we need to get the unit into meters. So the very first conversion isn't really going to find out anything new. It's just changing the unit of wavelength from picometers into meters. For all of this, I'm going to try to use the proper dimensional analysis steps just to remain consistent, meaning I've got picometers that I want to cancel off, so that's going to go in the bottom of my conversion factor. I'm changing that into meters, and if you look up any metric conversion chart, you'll find that there are 10 to the 12 picometers in 1 meter, which means the wavelength in meters now is simply 8 times 10 to the negative 12th. I'm going to keep track of all these things officially up at the top. 8 times 10 to the negative 12th meters is my wavelength. Now again, I needed those meters to actually start doing calculations, the first of which is going to be the frequency of this wave. Frequency, of course, is the amount of waves, the number of waves that pass a certain point. If you imagine this wave like traveling in a certain direction, how many waves pass through a certain point in 1 second. The units on these frequencies are typically just that, 1 over seconds, written sometimes as seconds to the negative 1, or also sometimes you'll see this as hertz. So those are all synonymous with each other. Let's swap colors here to help us keep track of what's what. To do this, we need an equation that takes the wavelength times the frequency and sets it equal to the speed of light. So that equation often looks like this, where that first symbol is a lambda, that's your wavelength in meters. This little V looking guy is a Greek letter nu, and that's the frequency in hertz, or 1 over seconds. If you multiply those two values together, they always equal the speed of light, this constant c, which is usually given to you. You can look it up, and that's 2.99 times 10 to the 8th meters per second. You can see why we needed the units of that wavelength to be in meters, because the speed of light that you plug in has units of meters. So you want to keep all your units consistent when you're using equations like this. 8 times 10 to the negative 12th meters is what I plug in for the wavelength, and now I can solve for the frequency by dividing both sides by that wavelength. 8 times 10 to the negative 12th. 8 times 10 to the negative 12th is going to cancel it off and leave me with the value for frequency. And I got 3.74 times 10 to the 19th. Notice how the meters is going to cancel off, so that's going to leave you with the units we want. 1 over seconds, seconds to the negative 1, or hertz, however you want to put it. Let's write that in officially up here. 3.74 times 10 to the 19th hertz. Next thing we can do is solve for the amount of energy that one photon of this wavelength, or with this frequency, how much energy one single photon is going to have. To do that, we have a different equation. E equals h times nu. That is E, the energy of the photon, the thing we're going to solve for. H is a constant called Planck's constant. You can look it up. And the nu, of course, is the frequency that we just solved for. So let's label, sometimes I like to label the E with E sub photon, just to help me remember what it is. Planck's constant is an insanely tiny number, 6.626 times 10 to the negative 34 joule seconds. And the frequency, of course, is that number in green that we just calculated, 3.74 times 10 to the 19th, 1 over seconds. All you got to do is simply multiply those two numbers. Notice how seconds are going to cancel off in the units and leave me with an energy of 1 photon in joules. And when you multiply those two numbers, you should get 2.4 let's see, 2.478, that's got an extra sig fig in there, but that's all right, times 10 to the negative 14th joules. So that's a very tiny number, but it should be because this is just one singular photon here, so we're kind of expecting a very tiny number. Again, let's write that in up here, 2.48 times 10 to the negative 14th joules. And then our very last conversion that we're going to make is to say, okay, so that's just one photon. Just like most times in science and chemistry and particle physics especially, there's rarely ever just one single photon, one single particle. There's lots of them, and we often use moles to keep track of the quantities of these particles. So for this guy, instead of just one photon, what about if you had 1 mole of those photons? How much energy would that have? And we're going to get this in kilojoules as well. There's no equation for this. It's simply taking the 2.478 times 10 to the negative 14th joules. You could put that joules over photons if you want to sort of get at what this is, right? This is the energy of one single photon. And all you got to do to find the energy of a mole of photons is multiply it by a mole. 6.02 times 10 to the 23rd. You're just scaling that up by however many particles a mole is. Since I'm running out of space here, let's jot that down up top. 1.49 times 10 to the 10th joules per mole of photons. Again, the only difference here is that we want to get this into kilojoules, and that's because these are generally going to be large numbers, so kilojoules makes more sense for a big number. So to switch it over, we just have to cancel off joules, top to bottom, and change that into kilojoules. Of course, 1 kilo anything is 1,000 of that thing. Joules is no different, so we're here really just dividing by 1,000. So when we switch it over to kilojoules officially, here's what you get. I've got this in, in long standard form. It's 14 million kilojoules, so it's still a huge number, but not quite as big. And I suppose we should probably switch that over to scientific notation just because of how big it is. 1.49 times 10 to the 7th kilojoules per mole for the final answer. That wraps it up for this video. Thanks a lot for watching.